Hi, I'm Mateo Salazar.
Hi, I'm Caleb Kafka.
Hi, I'm Jose Acosta.
Hi, I'm Sheridan Grant.
Hey guys, you want to play soccer?
Yeah.
Awesome.
How do I stop that? No. Okay.
Now your turn.
Whoa, I want to know the dynamics behind that.
Hey, let me show you.
Here are the dynamics behind the soccer ball without settling. If we look at this diagram to the left, we see that at the max height of the throw, the velocity is equal to 0, but it's at some height. And right before the ball is about to hit the floor, it has some velocity too, but the height is equal to 0. So when we use energy equations, the T1 and U2 go to 0, and we get U1 equals T2. And with canceling out the m's of U1 and T2, we get a final equation for square root of 2GH1 equal to V2, the velocity right before it's able to hit the floor. And we also know that the coefficient of restitution of a flat wall collision of a ball, E equals negative V2 over V1. But we could look at the diagram to the right and see that the velocity right before it's able to hit the floor is V2, and the velocity right after it hits the floor is V3. So we could rewrite the equation E equals negative V3 over V2. And we could solve for the exit velocity by being E equals negative V2 equal to V3. And with this knowledge, we could look at the momentum of the ball and use the momentum equations. And we see that it turned into mv2 plus the integral of 0 to the time of the collision, weight dt equals mv3. Replacing v3 with the derived equation we know, we could solve for E, but we know that since the collision is almost instantaneous but never 0, the coefficient of restitution is going to be very close to 1 but not 1. And with that, we were able to find the velocity at 3, because we could resolve as described above, and we get negative E v2 equals v3. Plugging that exit velocity, or getting that exit velocity, we're able to use energy equations again, T3 equal to U4, and we see that the masses cancel out again, and we're left with V3 squared over 2 GH4. Solving for H4, we're able to find the max height. And this goes to show that without settling the ball will continue to bounce until we have learned to settle the ball. And this is the dynamics behind settling the ball. We see that if we settle the ball, it would have no exit velocity, and we can use momentum equations again to see that L1 plus the impulse equals L2, and since we don't want the ball to bounce, we know that there's not going to be an exit velocity, so V2 would go to 0, and we get the same relation that the weight is the force in the integral of the impulse. So we could solve for T, and then we get this equation for time, and that's the best way to stop the ball without it bouncing.
Whoa, bro. That was pretty dynamical, huh?
Yeah,